Hi, this is Dr. Daw, and it's September 3rd, and we had class this morning at 11 o'clock. We covered complex numbers, and we had a demonstration in class of atomic spectra. The audio, for some reason, on the Zoom recording didn't take, and there's only the video part, so I thought I would go through what I did in lecture today because it's important, and also it completes the recordings. I want to have a complete set of recordings of this class. And so this is the to go in place of the Zoom recording. I'll make this available as well. So we're covering what I call chapter M. Let's see if I can write that better. Chapter M, which is a chapter on some mathematics that we're going to use. It comes between chapters 1 and 2 in the text. And in particular, I'm going to talk about complex numbers and complex variables, complex functions. It's the beginning of a very interesting subject of study, complex analysis, which I highly recommend, especially if you're going to be going into deeper levels of physics. We're using it at this point because it makes a very compact way to represent wave behavior. And the Schrodinger equation that we're going to study in chapter 2, which is an example of a wave equation, one of many wave equations, is written in complex form ordinarily. And so it's going to be much easier for you to understand Schrodinger equation if you understand complex numbers at some level. And so the next couple of homeworks deal with that. Okay, so now there's part of the assignment has been to read the appendix to the article by Dr. Rizzi called What is Math Really? And the appendix introduces complex numbers, but the entire article is about the development of mathematics from the beginning, which is, of course, what you know, which is quantity. That's the base property of physical things. Physical things have extension, have shape, which is the boundary of extension, and have parts, and these things are, of course, the beginning of number, beginning of geometry. So the roots of mathematics is in this basic property of physical things. It's the reason why math works so well in physics, because we're studying these kinds of properties which are close to quantity or similar to quantity in ways we've talked about before. Okay, so in that article, he shows how the axioms of arithmetic come from. Yes, axioms of arithmetic as a mathematical subject come from quantity and the properties of and the aspects of quantity that we start to consider. And so he develops the real number line. And so understanding of negative numbers, integers, negative numbers, rational numbers, irrational numbers, and the meaning of this number line and how to deal with that axiomatically in terms of operations like addition, multiplication, and so forth. All of that's developed in that article very rigorously. At the appendix now, he's also introducing complex numbers, and he introduces it as a way of dealing with a kind of second dimension. That is, we want to extend outside of one dimension, that we could represent this using complex numbers. Now, you've studied vectors in previous courses, and the vectors are a way of extending to multiple dimensions, 2 or 3 dimensions very easily. Complex numbers were developed as a way of doing this. So it's a different way to do it. It's now not the subject, the way we teach how to deal with multiple dimensions. But complex numbers themselves are still very useful. And as I said, you'll see how in a little bit here when we get to the relationship between complex functions and trigonometric functions. And you'll see how that works and how that's related to wave-like things and the discussion of waves. So he he talks about then having a complex number as a combination of two directions, and we have an index or a symbol I, which is going to signal that this second number here, x and y are two real numbers. The second number is the second of a pair, and it goes in the perpendicular direction, perpendicular to the x-axis. And so we can combine numbers like this. So a number like this then would be represented in terms of its coordinates, x and y. If we go over to the right x and up y, then we get to the number on the complex plane z. And so we designate these pieces here. Then the real part of this complex number is the x, and the second real part is the imaginary part. The second part is y. We drop the I from this, so the imaginary part is the y, not IY, but the y. Okay. And so that's the designation of these symbols, real and imaginary parts. And we also talk about some special things like z star is the complex conjugate of z, which is formed by flipping the imaginary part to its negative. So if z is up here, z star would be down here. It's the same real part, but the opposite imaginary part. And you can see you can form z plus its complex conjugate divided by 2 would then be x. And z minus its complex conjugate divided by, well, let's see, I better hold off on that because I'm about to divide by I, but I want to wait a minute because I don't want to introduce multiplication and division by I yet. So there's going to be a corresponding combination of z and z star that will give me the y part, but I'm going to hold off on that here for a second. I guess you could do this much. Z minus z star is equal to IY. There we go. That works. Okay, so and you can verify that just by doing this. We're going to talk about adding numbers though, and so I am getting a little bit ahead of myself. So how do I add these complex numbers? So suppose I have two numbers, x plus I, y, and another complex number. I can add them, and then the addition of this is closed on. I'm sorry, the complex numbers are closed under the addition, meaning that if I add these two numbers, I add the corresponding real parts and imaginary parts like this. So I have a new complex number with those corresponding real and imaginary parts. And so the real part of z plus u is in fact equal to the real part of z plus the real part of u, real part of u. And likewise for the imaginary parts. We also talk about the absolute value of a complex number. This is the distance of where we are on the complex plane from the origin. And using the Pythagorean theorem, that's just the square root of x squared plus y squared. And we also talk about the argument of x plus iy. And this is the arctan of xy, and the arctan, the argument, is just this angle here. So this distance is the absolute value. And this angle here is the argument. Absolute value is also written like this. For a complex number, that symbol is the same as abs. So notice that I wrote the arctan here. It's usually you've probably been used to writing the arctan of y over x, but I haven't written it that way. And there's a reason for it, which I want to make you aware of. It's not going to occur a lot here, but it's helpful for you to think about this. There are 4 quadrants. The complex numbers are drawn up into 4 quadrants here, which correspond to the signs, signs, S-I-G-N, of the numbers x and y. So quadrant 1, up in the upper right-hand corner, the real and imaginary parts are both positive. Quadrant 2, the real part is negative, but the imaginary part is positive. Quadrant 3, both are negative. Quadrant 4, real part is positive, but the imaginary part is negative. So notice then if I have y over x for quadrant 1 is positive because y and x are both positive. Y over x in quadrant 3 is positive. And so you cannot, based on the ratio of y to x, determine whether you're in the first quadrant or the third quadrant. But the angle would be different because we would have, for a number in the third quadrant over here, the angle would be greater than pi. Now notice that the angle that we use is always in radians. And so I may sometimes slip and talk about 45 degrees, but I really should be talking about pi over 4. You should use radians. And everything that I'm going to write in terms of the equation will be based on theta using radians. So the full circle is 2 pi. Half a circle is pi, and so forth. Okay, so if I'm looking for the angle here expressed in terms of x and y, then you can see if I take the arctan of this ratio y over x, I can't tell whether I'm in the first or third quadrants. And so that's why I write it this way. I'm generalizing the function now, and this function actually looks at the signs, SIGINs, S-I-G-N-S of x and y to determine which quadrant it's in. And so this is that angle, theta. And theta then could be chosen to go between 0 and 2 pi, for example, or between minus pi and pi. The range of the angle theta is the choice. I'm not going to belabor that today, but it's connected. These two things are connected. So I put this, I make this so you will learn it properly and not some ways you're going to have to generalize later. We're not going to make a lot of use of these distinctions in this class, but these basic things, argument, absolute value, real and imaginary parts, all of this, addition of complex numbers, all of that still follows. Okay, so now we bring up the question about multiplication. We're developing an arithmetic for like an algebra based on these complex numbers, which is going to be a generalization of what we're doing with regular numbers. And you'll see the application of that here in a minute. And so we're going to want to have something like multiplication and division. And then how do we talk about multiplication? So Dr. Rizzi introduces this idea that since we have this complex number like this, that the second part, iy, well, what if we were to take the number 1 along the real axis? And now I'm going to write real and imaginary here to emphasize that one is the real axis and one is the imaginary axis, and this is the complex plane. So let's write down, before I do this, let's write down a few numbers here. 1 plus I would be up here. 1 minus 1 plus I would be over here. Minus 1 minus I is over here. Down here is 1 minus I, and so forth. So, and we have another number up here, which is just I, like this. And so what if we were to start to multiply a real number with a complex number? In other words, we have 1 and we multiply by I, which is a complex number, and that should just give us I. So multiplying by I is like taking 1 and rotating it up here by, I should write this over here. Rotating it like this by pi over 2, 90 degrees, up to the imaginary axis. Okay, so then if we multiply again by I, so now we think of multiplication by I as like rotation by, in the counterclockwise direction, by 90 degrees, pi over 2. If we were to multiply again twice, then that would take 1 through I now to -1. So that would say then that I times I, which is what we mean by I squared, would be equal to -1. And so we have this thing here that we're talking about, which is like the square root of -1. Now this thing can't exist, right? Remember that even the use of the word square indicates something, right? Suppose I have a square of length A, side A. The area of the square is A by A because I take this length, sweep it perpendicular to itself, and that sweeps out an area. And the area is then going to be A squared. And you see the use of the word square to go along with the power 2. We do the same thing with a cube. Let's take this area now, sweep it perpendicular to itself, so out of the plane of the figure here towards us by another distance A. And now the volume will be A cubed, and notice the use of the word cube to go along with the power 3. So see how we're using this and when we're talking about the second power and the third power, we're talking about square and we're talking about cube. So these things are, the powers are themselves coming from that kind of aspect of extension, that there are 3 dimensions in what we're dealing with. We don't have a corresponding word for the 4th power. There's square, cube, then we just say 4th power because there is no sort of extension in 4 dimensions in the way that we're talking about the others. But now we can't have something which has negative area, right? Area is always a positive thing. So this thing, which is the square root of -1, is an odd thing, and it's clearly a being of reason. It exists only in the mind, not in the world. I can't take I, put it on the table, and let you have a look at it. It's a construction, a mental thing constructed to facilitate a mathematical formalism. And I think he describes that. Okay, so now let's continue this though. If I multiply again by I, so I started with 1, multiply by I, we get to I again, we get to -1. Another one will get us down to -I, right? So I cubed, get that? I cubed is going to be the same thing as -I. And finally, I to the 4th brings us back to 1. So I is like the 4th root of 1. And we'll find out there are 4 roots to that equation, but it's one of them. I is one of them. Okay, so now we can talk about multiplication. Take 2 numbers, x plus I, y, 2 complex numbers, u plus v plus I. And I can multiply them out. We want to make this arithmetic distributive of multiplication over addition. So we get 4 terms, and we want to retain the I, excuse me. And I'm going to move it out front. We're making this commutative. So I can always pull the I out front. So the order doesn't matter. So I'm going to, by convention, pull the I out when there's an imaginary term. I'm going to pull it out. So notice that we're producing another complex number here. It has a real part, which is this. And it has an imaginary part, which is this. And so it's a complex number, and that's how you do it. So notice then if I take x plus iy and I multiply by z star, I get x squared plus y squared plus no imaginary part. Z times its complex conjugate is in fact the square of the absolute value of z. Because the imaginary part here drops off. If you write out these 4 terms, you'll get these 2 terms. You get x squared, and then you get iy times -iy, and the negative of I squared is 1. So you get, that gives you a y squared. And then you get 2 more terms, plus I yx and -I yx, and those cancel out. So there's no imaginary part left in this example. When you multiply a complex number by its own complex conjugate. Okay, so we've got, now we're developing the mathematics of multiplication, and we can talk about division here. It's a little more complicated to do division at this stage, so I'm going to postpone the division. We'll talk about it here in a little bit. But let me show you how this much can be put to use. Let's talk about an equation, the famous quadratic equation, and there are roots of this you memorized. This famous equation, which was developed, I think, about the time that these complex variables were being studied. And anyway, it does come up in the subject of this. So the idea is a second order polynomial like this has two roots. Normally, so this thing that's inside of the square root there is called the discriminant. If the discriminant is greater than 0, then we have two real roots. And that means, what I mean by that is the square root is the square root of a positive. And so we have two values here. I'm going to put plus and minus. Remember, the plus and minus here is a shorthand for two numbers. There's the number with the plus sign combination, and then there's another number with a minus sign combination. So the two roots are minus b over 2a plus or minus the square root of delta over 2a. Okay, so that means that the two numbers, these two numbers, two real roots, straddle this. So this is in the middle, and they're on either side. So on the real axis, we have here is minus b over 2a, and then we have plus delta minus delta over 2a like this. And so this separation is square root of delta over a, this distance between the two roots, and they straddle the value of negative b over 2a. Okay, now if the discriminant is positive, you have these two roots, and in fact, you can draw the parabola that this would correspond to if I'm drawing it as though a is positive here, so that the curvature is up. If a is negative, then you get the down-oriented parabola. And so these places where the parabola intersects the axis are in fact the solutions to this equation. So either x plus or x minus will satisfy this equation here. So if I substitute one of these back into here, use the x plus, then I'll get 0. If I substitute the x minus in here, I'll get 0. Either one will give you a 0. Okay, now, but what happens if this discriminant is negative? Then we have the square root of a negative number. And so we've just introduced a way of dealing with something like the square root of a negative number. So what is the square root of negative 4? Well, that's 2 times I. Now notice there are actually two square roots, right? If you're remembering things, that there are two square roots. And so I'm going to write this, there is the possibility that there's the negative 2i, because negative 2i squared will give negative 4. And so that is a possibility. So I'm going to choose the positive root here. When I'm writing square root, I'm choosing that one. Okay, so in other words, if I take 2i and I square it, I'll get negative 4. Okay, yes, that's true. Okay, so in other words, if I have square root of delta, but delta is itself negative, I could write this as this. And then the square root of negative delta is positive. So if delta is negative, I can write the square root of delta as an imaginary number. Okay, and then the roots here are now complex. So we have this part, which is still real, plus or minus I, square root of negative delta over 2a. So now the roots here are imaginary. They're complex. They have a real and imaginary part. The square root gives rise to the imaginary part because delta is negative. Okay, so now we can write down the roots, even though the quadratic equation has this negative discriminant. And what does that mean? Well, it means that if I draw the function, this parabola, with values of a, b, and c that give a negative discriminant, it means it corresponds to a parabola that doesn't intersect the real axis. So it could be a parabola up here. So I get complex roots to the quadratic equation. In fact, this is two complex roots to the quadratic. In fact, this is a general theorem of algebra, the fundamental theorem of algebra, that an nth order polynomial has n complex roots like this. And exactly how you find them is a challenge, but they do exist. And so let's look at a couple of simple examples here. Let's suppose we have, hello, there we go. This equation, x squared minus 1 is equal to 0. So a is equal to 1, b is equal to 0, c is equal to negative 1. So the discriminant now is b squared minus 4ac. Oops, c is minus 1, 4ac. And so delta is equal to 4, delta is positive. And so that gives us two roots. And so we would write that, put that into the quadratic relation, but we get the obvious solution. Just looking at x squared minus 1, solving for x, you would get x is plus or minus 1. And that would, and we would write that on the real axis then. We have here a 0, there's minus 1 and plus 1 on the x-axis. Those would be the roots of that polynomial. That's the thing where they have two real roots. Now let's study an equation. Just flip the sign of c here. Now delta is equal to negative 4. And the roots are now plus or minus I. Which you can see directly from the equation by pulling the 1 over to the other side. And then we have x squared is negative 1. So x is going to be either plus I or minus I. Let me check that here. I squared and minus I squared. So I squared, of course, we said was negative 1. But minus I squared also is negative 1 because negative 1 squared is 1. So both plus I and minus I are square roots of negative 1. They're actually two square roots of negative 1. Okay, so now how do I draw this? Well, I have to go onto the complex plane. And so in general, I will be able to draw the solutions of a quadratic equation, the roots of a quadratic, of a polynomial, second order polynomial, as 2 points on the complex plane. So this one has these 2 points, plus I and minus I. Okay, so what you notice here is that, in fact, in general, for this quadratic equation, for a quadratic polynomial like this in general, that there are, that if the discriminant is positive, there are actually two roots along the real axis. If the discriminant is negative, then the two roots are separated across the real axis like this. So they, in general, will have real and imaginary parts. Over here. And so they'll be separated like that. Pretty neat. Okay, so this makes possible then to study the roots of polynomials without having to constantly be careful about taking square roots and cube roots of and so forth of negative numbers. And so it allows us a facility to generate solutions of every polynomial. Okay, so now we're going to look at the following thing. I'm going to start studying functions of complex numbers. Now, you've studied functions of real numbers, and an example would be, for example, one that we're going to use a lot is an exponential. This gets used a lot in physics, and we're going to, it's not going to be an exception here. We're going to use an exponential, but we're going to make an exponential of a complex function, of a complex argument. So the power is going to be a complex number. But let's first start just with e to the x. Let's draw that. Okay, that's easy. That goes like this, right? Crosses 1 at the origin. E to the minus x goes the other way. So be sure to draw these functions in general with x going positive and negative. So don't just the right hand. Don't just draw just the right hand side of this. Draw the full range where it's appropriate. E to the x, negative x, excuse me, e to the negative x would come down like this. Okay, this is e to the negative x. Okay. All right, what would we imagine then for something? What would we imagine? I'm sorry, that's a bad pun. Well, what would we do if we were to try to define a function of where we have, say, an imaginary number in the power? Now, we've actually done this here already without being explicit about it by admitting complex numbers here. What we are looking for is complex solutions to this equation. So we've actually got a complex function there. Everywhere there was an x, we now substitute x plus iy, and we put that in there, or just z as a complex number. So we've actually got a complex function. Now notice in general, if z is complex, then so is the function. So if z is a complex number, so is az squared plus bz plus c, even if a, b, and c are real. That quadratic expression is itself a complex number. So in general, a function of a complex number is itself complex. So we anticipate that e to the iy is going to be complex. But now how do we go about defining such a thing and extending it from the thing e to the x that we got before? So the way to do that is to go back to the definition of e to the x. And I asked in class for this, and a student obligingly remembered this expression. Okay, as the definition for e to the x. And if I put x equals to 1, this is just the definition of e. The natural number limit is n goes to infinity. In fact, this was the definition. I started with this. Okay, this is the definition of e, and then e to the x follows as that. And this is an interesting number, has a lot of interesting properties, one of which, for example, this function e to the x, every derivative of e to the x is just e to the x. Remarkable function. Okay, so and I pointed out how do you get this? Then you can study this sequence here. Let's set n equals to 1. Then, and let's look at this expression here. I'm going to evaluate it for n equals 1, 2, 3, 4, and so forth. If n equals 1, then we have 1 plus 1 raised to the first power, so it's 2. The next one is 1 plus a half, so it's 3 halves squared. The next one is 4/3 cubed. The next is 5/4 to the 4th, and so forth. So if you actually do these with a calculator, you'll see that this is converging to the value of e, which is 2 point something. See, I'll remember this better than I do. I have pi better memorized than I do e. Okay, and then e to the x would be evaluated the same way. Instead of 1 plus 1 over n, I would use 1 plus x over n, and then I would keep increasing the number of n, and that will converge on a finite value, which is e to the x. So let's try the same sort of thing now for e to the iy. So let's suppose we define this, the function of a complex or an imaginary argument in this case. 1 plus iy over n raised to the nth. Now you know how to do this, right? You know how to multiply complex numbers together. 1 plus iy over n is a complex number. You know how to multiply it by itself n times. Big N is an integer. And so in principle, you know how to do this, no problem. So here's an interesting thing then, e to the I pi. Let's set y equals to pi. Here's a really interesting thing. Doing this sequence, like I said, this converges to -1. Very special equation. It shows a lot of interesting things about relationships between e and pi and 1 and I. It's a very interesting equation. And let's see, I want to show here, I'm going to pull away here to pull up my desktop and show you this. What I did here was after class, I did this. I want to show you what that looks like, that series. So here I have, let me pull this down. Here I have evaluated that series for n of 1, 2, 3, 4, 5, 6. So in each case, I calculate out the complex number, of course. I have a little program that does this, so I didn't actually do it to the 18th power. I actually did this on a program, but you can see how it starts off at 1 plus I to the first power, and then you increase n squared, cube, and so forth, and it's converging around here, and it's going to, if I go up above 20, now it will converge here to -1, asymptotically converge to -1. That's pretty cool. Okay, very interesting. Oh, what's going on here? Hang on a second, technical problem here. I want to get, here we go. All right, now I need to steal the screen back. Okay, there we go. Good. All right, so that's kind of an interesting exercise, and I suggest you give it a try or something like that. But this one is a special one of those. All right, so this is a special case of a more general relationship called the Euler relation. Euler being a famous, very capable German mathematician. The Euler relation, which is that this exponential of an imaginary argument can be written, of course, it's a complex number. But the real and imaginary parts are very simple. They're cosine and sine. Okay, now we plotted the exponential of a real argument here. How do we plot the exponential of an imaginary argument? Well, it's a complex valued function. It has a real and imaginary parts. And so we can plot those real and imaginary parts separately. So one way to do it would be to plot as a function of y, the real part of e to the iy, which is just the cosine, like this. Okay, usual cosine function. And we could, on a second plot the imaginary part, which is just the sine. Okay, and then so we'd have to have two plots. You could try to, if you get really good at this, after a while, you can put these two together. Maybe you draw the real and imaginary parts with, one's with a solid line, and the other one is with a dashed line, like the real part looks like this. And the imaginary part, maybe you draw it in some other color. Okay, so forth, like this. So, something like that, you might get away with trying to put them on the same plot, but you'd have two curves. But until you start to getting more comfortable, maybe you just draw them separately like this so that you recognize that there's two different pieces. Okay, now remember the trig functions are wavy. Notice that word, wavy. They wiggle around like that, like waves. And we're going to find that the trig functions are very handy functions in describing solutions to wave equations. And now we have an interesting relationship between the exponential of an imaginary argument and these trig functions. And so now this is getting to be something very interesting here. Now you'll begin to understand why it's a very compact way of writing solutions to the wave equation. That's what we're going to. And so it's not at all surprising that we'll find complex numbers to be a convenient way of compactly writing solutions to wave equations. And so I'm just hinting at what's coming up. Okay, so let's go and look at this then. Let's go back to that relation. Okay, so we have a complex number, x plus I, y, like this. And we said this distance here was the absolute value. I'm going to call that r. And this angle theta. And so we're relating it to what's also called polar form, polar notation. So the coordinates x and y of a point on the complex plane can be expressed in terms of the distance r, which is the absolute magnitude of the number square root of x squared plus y squared, and also the angle. So instead of giving the, say, so far east, so far north, you say, well, put your heading at some angle relative to east, 20 degrees above east. There we go with degrees again. And then go some distance from here and with that heading. So that's another way of doing it, the polar coordinate fashion. So there's a relationship between x and y and r and theta. And in fact, that's what I was talking about before when I talked about the absolute magnitude and the argument was this relationship. And you can go backwards. If you know r and theta, you can go backwards. So if you know r, x is r cosine theta. If you don't know r and theta, you can get x and y. Oh, wait a minute here. Here's the cosine and the sine. We just had e to the I theta is cosine theta plus I sine y, I sine theta. We had, instead of theta, we had y, but here that's e to the I theta is this. Let's multiply by r cosine theta plus I r sine theta. And now this is x plus I y. And that's the way we wrote the complex number before. Now we have a new way of writing the same complex number. So these two ways of writing the number, which are equivalent but different, this is called the Cartesian form because it resembles the Cartesian coordinates, uses those which have the two orthogonal axes, east and north, or horizontal and vertical. And then we have the polar form. So we have two different ways of writing complex numbers, either Cartesian form or polar form, which accomplish the same thing. And the polar form is based on the Euler relation. So I can write down the polar form for a complex number, and so you should be able to write down complex forms like that. So let's suppose here is a complex number, 1 plus I. Let's do some simple ones first. What is this in polar form? Well, this is easy, right? This one's easy. This is just 1 times e to the I 0, because the angle is 0 and the distance is 1. How about I? Well, it's still a distance 1 from the origin, and the angle is pi over 2. Can you see that? If I go back to my complex plane, this angle is pi over 2. So I is just the same as e to the I pi over 2. And again, that's a special case of the Euler relation. If I substitute pi over 2, there I get cosine of pi over 2 is 0, sine of pi over 2 is 1, so I just get I times the sine of pi over 2, which is I. Then we see back to this relation, e to the I pi. Well, now that's a special case where the angle is pi, so we go all the way around. E to the I 3 pi over 2 is negative I. E to the I 2 pi, go all the way around, comes back to 1. How about if we have something like this, pi over 2, it's a distance 1 from the origin at an angle of pi over 4. So e to the I pi over 4. That's going to be equal to what? Okay, so it's cosine of pi over 4 plus I sine pi over 4. So it's 1 over square root of 2 plus I 1 over square root of 2. So the x component is 1 over square root of 2. The y component is 1 over square root of 2. Okay. Or you could write it this way: square root of 2 times e to the I pi over 4 is equal to 1 plus I. That would be out here. That would be a distance farther out here. Now we're distance square root of 2, and that goes from 1, has coordinates 1 and 1, like this. Okay, you're starting to see how this works now, right? This is the magnitude. So the magnitude is just the thing out front. The argument is just the angle. The real part of the polar form is then just r cosine theta, and the imaginary part is just r sine theta, written in terms of the polar coordinates, like that. Multiplication is easy in polar form. If I have two complex numbers to multiply in polar form, it's really easy. R1 e to the I theta 1 times R2 e to the I theta 2. So Z1, Z2. In polar form, I multiply them together, and it's and because the multiplication and addition have been developed to be very similar to just multiplying and dividing complex just regular numbers, it's all commutative, all these things. It makes this easy. The answer is just this: the product of the pre-exponentials there, the R1, R2. So this is now a new complex number whose absolute magnitude is this and whose argument is this. If you have it in polar form, then the product is very easy. The ratio is very easy. It's just R1 over R2 e to the I theta 1 minus theta 2. What could be easier? Okay. Let's see. I think that's where I ended up today. And I'm pretty sure. I'm trying to remember if I did. I don't think I did anything more than that. So you're going to have some part of your assignment is to become familiar with using these complex numbers and to manipulate them in this fashion and to understand them. And we're going to use these complex functions as hinted at over here to study wave-like solutions. And they'll be very handy for us. And so we're going to do some exercises with these complex functions. We'll also study some things like simple harmonic motion, because wave motion resembles harmonic oscillation in some ways. And so we will study solutions to this equation. And we'll make use of complex numbers to help us solve this equation. And this equation, of course, you should recognize it as the Newton's second law written down for a body attached to the end of a spring like this, a body of mass m attached to the end of a spring constant k. What if we put this thing into a viscous medium? So there's also a drag. So in addition to the spring force, the force that the spring exerts on the mass, suppose also that there's a drag, which is proportional to the velocity, the drag force. So there is a drag coefficient, gamma. And so this is what would correspond to having this mass on the end of a spring moving in some kind of like shampoo, prel, some kind of viscous medium. And it's going to dampen the motion. And so this is called the damped harmonic oscillator. This is called the simple harmonic oscillator. And we're going to study solutions to this equation, these two equations, in terms of complex numbers. And also then we're going to study solutions to the wave equation. I'm going to discuss the wave equation here. Wave equation comes in the course of this sequence from electromagnetic waves. So we're going to study wave equation we get from E and M. But there are also other wave equations. We're going to develop another one called the Schrodinger wave equation. So we're going to make use of complex variables, complex numbers to develop solutions to these equations. And so that's what's coming. All right, I think I've covered everything I wanted to do today, and I'm going to, as I said, insert this into the sequence of recordings. So this will become part of the sequence of recordings for this class.